Team C, formed by Jorge Luis Chimal, Carlos Michel Santiago, and myself, Carla Sofia Padilla. We would like to introduce our innovating project, a nutrient control system for aquaculture tanks and aquariums that is called AquaBalance. Aquaculture is a sector dedicated to the culture and harvesting aquatic species like fish, crustaceans, and aquatic microorganisms like microalgae under controlled conditions. That's why it's essential to maintain adequate control of the environment where the aquatic species are grown. Constant monitoring is essential to detect the quality of the water to avoid any negative effects on organisms. The leading country in this sector is China, and it's noted that 17 to 18% of fish products in the world come from Europe and America, meaning that aquaculture is an important sector with continuous growth. Our objective is to build a water quality control system by using a conductivity sensor, a peristaltic pump, and a delivery system so we can control and monitor the nutrient concentration in aquaculture tanks or conservation aquariums.
Okay, our control system required for an aquaculture tank, a pool, or an aquarium consists of certain parts. First of all, we have our computer, which is used to generate the code and to upload it to our Arduino board. Here is the terminal where we can see the measurements. Then we have the Arduino board, which is connected to our relay and to the conductivity sensor. The relay is also connected to this adapter and a power source that will provide of 12 volts and direct current. Then we have a peristaltic pump, which will be used to pump a solution containing 1,000 parts per million of sodium chloride, and this one will provide with the necessary amount of salt to reach a defined concentration, which in this case for our demonstration is of 200 parts per million. In order to maintain an homogeneous solution, we have a steering plate and also a magnetic steerer. The sensor is placed around in the central part of the beaker in order to obtain accurate and precise measurements. Here also we have the hoses, which are used to transport the fluid. Before showing you our working project, first we will briefly describe our implemented code. First, we start with defining the pin corresponding to the TDS sensor, the total dissolved solid sensor. Then we define the reference voltage as 5 volts, and then we use this count variable to define the number of samples that we will filter before we get an actual value. Then we have the defined variables as the buffer to generate our arrays where we will store the readings. Then we initialize the variables corresponding to the average voltage, the TDS value, and the temperature that we will use for compensation. Then we use a median filtering algorithm, which will give us a stable TDS value from the array of readings. Then we use the void setup, where we define 115,200 as the baud rate, and then we define the TDS sensor pin as the input, while the pump pin corresponds to the output, and we define that it will start being off. Then on the loop, we define that we will update the analog buffer every 40 milliseconds, and then we define that we will measure and print every 0.25 seconds. Then we will copy the analog values to a temporary buffer to process them, and then we use the median filter to convert to voltage. Then we compensate for temperature, we convert the voltage to the TDS value, we calculate the elapsed time in seconds with the fractional part, and finally we print the time and the TDS value in parts per million. Here at the end we have the pump control based on TDS value, meaning that when the TDS value is lower than 300 parts per million, the pump will be on, will be functioning. When the value of the TDS exceeds 300 parts per million, the pump will stop functioning.
previously mentioned, one of the main applications of these types of systems is in the growth of microalgae and fish in aquaculture. What we have here is a simulation of a bioreactor, which we will inoculate with 5% of the working volume, which is 200 milliliters. So the 5% equals 10 milliliters here, which we will be adding to the bioreactor. One of the main metabolites of interest in Chlorella sorokinana is ergosterol, which is used for the inhibition of cancer cells. To reach the maximum concentration of ergosterol, we have to adjust the sodium chloride solution to 300 parts per million to achieve the production of this metabolite of interest.
Here we're simulating nutrient uptake. The peristaltic pump draws the nutrient solution into the system. Meanwhile, the salinity sensor continuously monitors the solution's concentration. If salinity is too low, the pump adds more nutrients to maintain the desired levels. When the target salinity is reached, the pump stops. As seen in this image, the transfer function of both systems was obtained. The normal configuration that consisted of only distilled water and sodium chloride solution was moderately stable as the poles are imaginary. The microalgae configuration was stable as the only pole was negative. Both systems presented an R² value greater than 95%, which shows a good fit. In conclusion, the project successfully achieved its objectives by developing a water quality control system that integrates a conductivity sensor, an actuator, and a delivery mechanism. This closed-loop system efficiently monitored and regulated salinity levels within a tank, demonstrating its functionality during testing. For example, in the microalgae culture simulation, the system maintained an optimal concentration of 300 parts per million for the production of ergosterol. Beyond the technical achievements, this project was a valuable learning experience, combining programming skills and electronic tools to create a reliable and functional solution for water quality management.